Right now, you are floating in a universe where stars explode more than once. Entire galaxies vanish into silent regions hundreds of millions of light-years wide, and brief signals arrive from the dark, releasing more energy in a heartbeat than our sun does in days. Invisible forces drag every galaxy in our neighborhood toward a destination we cannot see, while lonely planets drift through interstellar night without ever knowing the warmth of a sun. Tonight, we journey through whispers of radio energy that appear only once. Visitors from outside our solar system that bend around our star like engineered artifacts, and black holes that wander freely through space without a galaxy to anchor them. What does it mean to live in a cosmos where some mysteries pulse like messages, while others tower above us in silence, older and colder than anything we have words for? If you're ready to drift through the universe's strangest discoveries, like and subscribe and tell us where in the world you are listening from. Let's begin. Every so often, radio telescopes catch a millisecond whisper loaded with the energy of a week's worth of starlight. Some of these bursts repeat with eerie rhythm, as if following a clock hidden outside time. Others arrive once and are never heard again. Fast radio bursts, or FRBs, are short pulses of radio emission that typically last less than 5 milliseconds. They originate from extragalactic distances, with dispersion measures so large that their signals have traveled through billions of light-years of ionized gas. The earliest confirmed detection occurred in archived data from 2007, though the burst itself was captured in 2001. Its strength suggested a source capable of releasing as much energy in 1,000th of a second as the sun emits in several days. The distribution of events does not match local interference or instrumental noise. They arrive from random areas of the sky, with no preference for the Milky Way's disk or its halo. Some repeat. FRB 121102 emits bursts from a dwarf galaxy 3 billion light-years away, associated with a compact, persistent radio source. Others appear only once despite years of follow-up observations. Their behavior suggests multiple formation mechanisms, or at least multiple physical environments. The most widely accepted explanation involves magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. Their crusts can fracture, releasing energy that propagates through the magnetosphere and into space. When observed from Earth, the signal arrives as a sharp radio flash. Support for this model came in 2020, when a magnetar in our own galaxy, SGR 1935+2154, produced a radio burst orders of magnitude fainter than extragalactic FRBs, but still strong enough to serve as a structural analog. Other hypotheses remain active. Some FRBs show frequency drifts and polarizations that do not match magnetar flares neatly. Some emerge from environments with no obvious compact objects. A subset show quasi-periodic spacing, hinting at orbital motion or precession. The diversity of observations indicates that the phenomenon may not be the signature of a single astrophysical process. What makes FRBs striking is not their mystery, but their scale. They travel across cosmic voids, through intergalactic plasma, and past the gravity wells of galaxy clusters, yet their structure persists clearly enough to be decoded. A signal formed in a moment crosses billions of years to arrive here with millisecond precision. The universe has no shortage of energy. Some of it speaks in brief sentences we are only beginning to translate. On August 15th, 1977, the Big Ear telescope caught a narrow radio beam from deep space, tuned precisely to the hydrogen line. It lasted 72 seconds, then vanished forever. Jerry Amon circled the numbers on the printout and wrote a single word: wow. Fast radio bursts were unknown at the time. The wow signal did not resemble background interference, lightning, or reflections from Earth. It arrived at 1,420.4556 MHz, within a fraction of the neutral hydrogen line, an internationally protected region of the radio spectrum, where terrestrial transmitters are forbidden. The Big Ear telescope used a drift scan technique. As Earth rotated, the sky passed over the fixed instrument. A true celestial signal would enter one of Big Ear's two feed horns, peak, then fade with a characteristic pattern as the beam moved on. That is exactly what the WOW signal did. The hydrogen line is a natural frequency emitted when electrons in neutral hydrogen flip their spin. It is important in astronomy because hydrogen is the most abundant element in the universe, and the 21-centimeter wavelength passes easily through interstellar dust. Any civilization attempting long-distance communication might choose it intentionally because it stands out against cosmic noise. The WOW signal was extremely narrowband, spanning less than 10 kilohertz. Natural astrophysical radio sources, pulsars, quasars, supernova remnants, spread energy across broad bands. A narrowband emission indicates a tuned transmitter or a physical mechanism not known in natural environments. Its intensity peaked at about 30 sigma above background, meaning it exceeded noise expectations by a factor large enough to rule out statistical fluctuation. The signal lasted the exact length expected of a celestial source drifting through Big Ear's beam, roughly 72 seconds. It did not appear in both horns, suggesting a single point in the sky rather than multipath reflection. When the telescope returned to the same region minutes later, it was gone. Follow-up campaigns continued for decades, using stronger receivers, wider frequency ranges, and higher resolution. No repeat was ever found. Attempts to tie the signal to comets or passing objects have not been consistent with its power, spectral precision, or lack of Doppler drift. The hydrogen line should shift if the object were nearby or accelerating. The WOW signal exhibited no detectable shift. Because of its singularity, scientists treat the WOW signal as an outlier, a data point without a second example to form a population. The simplest artificial transmission would need a transmitter power equivalent to large terrestrial radio arrays. At distances of hundreds of light years, that requirement becomes orders of magnitude greater. Natural explanations have been proposed, but no model reproduces the event's narrowband and strength simultaneously. The region of sky, near the constellation Sagittarius, contains no known astrophysical source capable of emitting such a signal with that spectral profile. The printout still exists, a row of numbers marking a signal that arrived once and never returned. Nothing more was ever heard from that patch of sky. The universe offered a single sentence, and then it fell silent. It arrived from interstellar space, tumbling like a shard of metal, accelerating without visible jets or cometary tail. Its brightness changed strangely, as if reflecting sunlight from a flattened surface. It came once, bent around the sun, and disappeared without leaving dust or debris. Oumuamua was the first confirmed macroscopic interstellar object ever observed passing through our solar system. It was discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Its trajectory could not be reconciled with any bound object. Its inbound velocity relative to the Sun was around 26 kilometers per second, exceeding gravitational capture criteria. Instead of orbiting, it followed a hyperbolic path with an eccentricity of about 1.2, crossing inside Mercury's orbit and then departing toward the outer dark. The object did not match known asteroids or comets. It reflected sunlight strongly, yet failed to produce the coma or tail expected from ices vaporizing near the Sun. As Oumuamua moved away, its speed increased slightly, a non-gravitational acceleration inconsistent with radiation pressure alone. Most comets accelerate due to outgassing, ice vaporizing into jets that push the nucleus forward. Instruments detected no such emissions. The acceleration was weak, on the order of 10 to the power of -6 mem s squared, but persistent. Its light curve was also unusual. Instead of stable periodic reflection from a roughly ellipsoidal body, the brightness varied by a factor of 10, implying either extreme elongation or a thin, flattened geometry. Estimates placed its aspect ratio at 5 to 1 or greater, significantly beyond typical asteroid shapes produced by impacts or rotational deformation. Spectral readings suggested a neutral or slightly reddish surface, similar to irradiated minerals found on outer solar system bodies. Measurements showed no carbon dioxide, carbon monoxide, or water vapor signatures. The lack of dust was equally notable. No trail, no debris cloud, no ultraviolet emission. Observations lasted only a few weeks. By the time astronomers mobilized larger telescopes, its brightness had dropped below effective detection thresholds. Radar could not be used because the object was already too far and too faint. The record is therefore a combination of photometry, astrometry, and trajectory modeling during its brief passage. Multiple hypotheses attempt to explain the anomaly. One model proposes a nitrogen ice fragment similar to a planetary crustal shard from a Pluto-like world. Nitrogen sublimation could provide thrust without visible dust. Another suggests hydrogen ice, which would accelerate efficiently but evaporate too quickly to survive long interstellar travel. A third interpretation considers fractal aggregates, porous bodies formed in protoplanetary disks capable of producing high acceleration with minimal mass. None fully satisfy the observed geometry, optical behavior, and trajectory simultaneously. A thin sheet composition remains mathematically consistent with the acceleration, though no known natural process reliably forms sheets tens to hundreds of meters long in vacuum. Oumuamua crossed the solar system once, leaving only measurements and questions. No spacecraft will ever reach it. Its path suggests there have been others like it, moving through interstellar space unnoticed, passing between stars without intention or warning. Not all black holes sleep in the centers of galaxies. Some drift through empty space, invisible except for the way they distort the starlight behind them. They move like predators with no territory, hunting only by the gravity they leak into the dark. Most stellar black holes remain bound to their birth environments, binary systems, stellar clusters, or galactic disks. A smaller subset do not. These are rogue or isolated black holes, compact remnants no longer gravitationally attached to any nearby matter. In the Milky Way alone, population models suggest tens to hundreds of millions of such objects. They emit no light and have no accretion disks, unless they encounter gas or a passing star. In empty interstellar space, they are effectively undetectable, moving silently along trajectories set long ago. Several processes can eject a black hole. The most common is natal kick, an asymmetric supernova that imparts velocity to the collapsing core. When a massive star's explosion is uneven, conservation of momentum pushes the remnant away at speeds that can exceed 100 kilometers per second. A second mechanism occurs when binary systems interact. If one star collapses, the sudden mass loss can destabilize the orbit, flinging the compact object outward. The third and most powerful mechanism arises during black hole mergers. Gravitational waves carry net momentum. When the emission is directional, the merged hole recoils, sometimes at more than 1,000 kilometers per second, fast enough to escape a galaxy entirely. Rogue black holes cannot be seen directly, but they reveal themselves through gravitational lensing. When one passes in front of a distant star, it bends the star's light, producing a smooth amplification curve that can last months or years. In 2022, a microlensing event near the galactic bulge showed no visible lensing source. Astrometric measurements from Hubble and Gaia indicated the deflector's mass at roughly 7 solar masses, moving through space at around 160 kilometers per second. No companion star was present, no accretion disk surrounded it. The only signature was the bending of the background starlight, consistent with an isolated compact object. A rogue black hole passing through a system does not announce itself. Its gravitational influence extends far beyond the event horizon, perturbing orbits long before contact. A star can be deflected or tidally disrupted. A planet may be ejected into interstellar space or drawn off trajectory in a slow destabilization that unfolds over thousands of years. If gas or dust enters its vicinity, the black hole may form a temporary accretion disk, emitting X-rays, as in falling matter heats. But in most regions of the galaxy, space is sparse. An isolated black hole will drift through the void for millions of years without interaction. These objects travel without light, without orbit, and without record of their origin. Their paths are written only in the curvature of space, and most will never be noticed at all. The universe contains them whether we find them or not. Your galaxy is not moving randomly. The entire local group, Virgo cluster, and thousands of neighboring galaxies are being pulled towards something colossal and unseen. Its gravity bends the trajectories of star systems like threads in a cosmic current, and we do not know what lies at its heart. In the 1980s, redshift surveys revealed that galaxies in our region of the universe do not simply recede due to cosmic expansion. They share a coherent, peculiar velocity. An additional motion superimposed on expansion directed toward the constellations Norma and Triangulum Australe. This region, approximately 150 to 250 million light-years away, is known as the Great Attractor. Our own Milky Way, the Andromeda Galaxy, and the Virgo cluster are all falling toward it at about 600 kilometers per second. This movement is not caused by a single galaxy or cluster, but by mass distributed across a large region of space, whose structure remains partially obscured by the plane of the Milky Way. Galaxies move under the influence of gravity across supercluster scales. Their velocities reflect the distribution of mass in the cosmic web. Where matter has accumulated, clusters, filaments, and superclusters, space becomes a basin into which galaxies slowly fall. The Great Attractor is not an active force. It is a gravitational, well formed by dense concentrations of galaxy groups. Observations suggest that the Hydra Centaurus region, rich in clusters and hot intracluster gas, plays a central role. X-ray mapping indicates massive structures spanning tens of millions of light-years, supported by dark matter halos, far larger than those surrounding individual galaxies. These halos curve spacetime smoothly, directing entire structures toward their center of mass. Direct imaging is difficult because the region lies behind the zone of avoidance, the dense, dusty plane of the Milky Way that blocks optical light. Infrared and radio observations have gradually revealed hidden clusters. The most significant discoveries point to the Norma cluster, Abell 3627, a massive assembly of galaxies roughly 220 million light-years away. Its combined mass is sufficient to influence the motion of nearby superclusters. Beyond it lies Laniakea, the largest supercluster to which our own galaxy belongs. Flow models show that local galaxies follow streamlines that converge toward the Norma region, forming a basin of attraction that extends hundreds of millions of light-years. The motion persists, even when corrected for cosmic expansion, implying gravitational origin rather than observational bias. The Great Attractor is not a single object waiting at the end of a path. It is part of a larger network of mass concentrations. As surveys expanded, astronomers discovered that flows do not terminate in the Norma cluster alone. They continue past it, toward the Shapley supercluster, a region containing some of the densest known galaxy concentrations within 650 million light-years. The implication is that our motion is not toward a point, but into a gravitational corridor carved by large-scale structure. On timescales of billions of years, galaxy groups will drift deeper into this basin, following trajectories that are effectively irreversible. Our galaxy is carried along this current with no means of escape. We do not choose the direction, and we cannot change it. The universe has already assigned our destination, even if we cannot see it clearly. Galaxy clusters across billions of light-years drift in the same direction, like leaves sliding along invisible water. Their motion does not match cosmic expansion or local gravity. Something beyond the observable horizon may be tugging them, pulling the universe toward a destination outside our reach. Dark flow refers to a large-scale movement of galaxy clusters that cannot be explained by gravity from known structures within the visible universe. Standard cosmology predicts that on scales greater than 300 million light-years, motions caused by gravitational irregularities should average out. Expansion dominates, and peculiar velocities become small and random. Yet when galaxy clusters were studied using the kinetic Sunyaev-Zeldovich effect, shifts in cosmic microwave background photons scattered by moving hot gas, researchers found a coherent drift extending over distances greater than 1 billion light-years. Hundreds of clusters appeared to be moving in similar directions toward the constellations Centaurus and Vela. If real, the behavior implies that gravitational influence extends well beyond the volume we can directly observe. The observable universe is limited by the cosmic horizon. Light has had only 13.8 billion years to reach us. Beyond that boundary may exist structures forming during inflation, when space expanded exponentially faster than light could cross it. During inflation, density fluctuations could have produced massive regions, superclusters or voids, far larger than any we can see today. Their gravity would still shape space locally, even if their light has never reached us. The motion detected in dark flow surveys would therefore be a relic of early structure, a pull exerted from outside our cosmic window. The initial evidence came from studies conducted using NASA's Wilkinson Microwave Anisotropy Probe. Researchers measured temperature shifts caused by galaxy clusters moving relative to the CMB. If a cluster travels toward us, photons passing through its hot gas are slightly blue-shifted. If it travels away, they are red-shifted. When the data were stacked across hundreds of clusters, a directional bias emerged. The signal pointed toward a region near the Centaurus Hydra area. Later analyses using different selection methods saw similar patterns, though with varying confidence levels. Attempts to tie the effect to known mass concentrations, such as the Great Attractor and Shapley supercluster, did not fully resolve the drift. Dark flow remains controversial. Some cosmologists argue that the statistical significance is lower than early papers suggested, and that observational noise may mimic coherent motion. Others contend that the effect is real, but reflects local mass distributions distorted by incomplete sky coverage. The most radical interpretation is that the observable universe is not representative of the whole. If energy and matter beyond the cosmic horizon are unevenly distributed, they could pull our entire region of space toward them. This would not contradict relativity. Gravity propagates through space-time, regardless of whether light from the source can reach us. The result would be a directional drift embedded in cosmic expansion, persistent over billions of years. If dark flow exists, it points towards structures we will never see, guiding our galaxy along a path laid before the first stars formed. The universe may contain destinations beyond every telescope's reach, shaping our motion without revealing their origin. In the constellation Boötis sits a cosmic wound 330 million light-years wide, with almost no galaxies at all. A place so empty that entire galaxy clusters would vanish inside it without leaving ripples. If the Milky Way lived there, we might never discover the universe existed. The Boötis void was first identified in 1981 by astronomer Robert Kirshner and colleagues while mapping galaxy redshifts. Instead of a uniform distribution of galaxies, the survey revealed a vast gap, a sphere of space largely devoid of luminous matter. Voids are common in large-scale cosmic structure. They form naturally as matter collapses into filaments and superclusters. But typical voids measure tens of millions of light-years across. The Boötis void spans more than 300 million light-years, making it one of the largest confirmed voids near our cosmic neighborhood. Its diameter is larger than the space between the Milky Way and the Virgo cluster, and its volume could contain tens of thousands of galaxies if matter were distributed normally. Cosmic voids arise from the distribution of dark matter following the Big Bang. Minute density fluctuations in the early universe seeded gravitational wells. Matter flowed toward overdense regions, forming filaments and nodes where galaxies would emerge. Regions with lower initial density expanded faster, becoming underpopulated cavities. Over billions of years, Small voids merge into larger ones, similar to bubbles coalescing in a liquid. The Botez void likely formed through this process, combining numerous smaller voids into a supervoid. However, even under this model, simulations predict that a region of its size should still contain thousands of galaxies. The observed population is a fraction of that number. Initial counts suggested the void contained only a single galaxy. Deeper surveys later found around 60. Even with these additions, the density is far below cosmic averages. Galaxies cluster at its boundaries, forming structures such as the Hercules and Corona Borealis superclusters, but the interior remains sparsely populated. Surveys using optical and infrared telescopes confirm the absence of bright galaxies, while radio observations detect no significant hydrogen concentrations. The void is not obscured, it is simply empty. Its shape is roughly spherical rather than filamentary, implying long-term stability rather than a transient gap caused by obscuration or incomplete mapping. The existence of a void of this scale challenges assumptions about large-scale uniformity. On cosmological scales, matter is expected to follow a fairly smooth distribution, with density variations averaging out beyond several 100 million light-years. The Botez void violates this expectation. Some models suggest it may be a relic of early inflation, where quantum fluctuations magnified beyond the reach of later gravitational smoothing. Others propose environmental effects, galaxies forming near boundaries rather than interiors due to interaction with nearby filaments. None fully explain the starkness of the void. If a technological civilization developed inside it, the nearest galaxies would be so distant and faint that cosmic expansion might seem negligible. Without external reference points, a cosmology resembling ours might never arise. The Botez void is not a scar and not an anomaly in the human sense. It is a region where matter simply did not gather, a silent space between structures. The universe does not promise uniformity, only the distribution that gravity allows. Maps of the cosmic microwave background show a region colder than it should be, colder than random chance allows. Some scientists blame a supervoid. Others whisper about collisions between universes. Whatever the cause, it sits in the sky, like a scar left from something we do not remember. The cosmic microwave background, or CMB, is fossil radiation from the early universe. It formed when the cosmos cooled enough, about 380,000 years after the Big Bang, for protons and electrons to bind into neutral hydrogen. Light that had previously scattered freely finally traveled unimpeded, leaving behind a nearly uniform glow at 2.725 Kelvin. Its temperature variations are tiny, on the order of microkelvin, and encode the density fluctuations that later became galaxies and clusters. In the southern hemisphere of the sky, toward the constellation Eridanus, one region departs sharply from expectations. It is colder than statistical models predict, and it spans hundreds of millions of light-years when projected into cosmic structure. This anomaly is known as the cold spot. If the universe were perfectly homogeneous at large scales, the CMB would show only small fluctuations caused by primordial quantum perturbations. The cold spot deviates from that pattern. One possible explanation is the integrated Sachs-Wolf effect. Photons passing through gravitational wells lose energy differently in an expanding universe. If they cross a large, underdense region, a supervoid, they may experience less gravitational blue shift on exit than they did falling inward, arriving cooler than expected. In this model, the cold spot is not a remnant of the early universe itself, but a byproduct of light traveling through a region of space with unusually low matter density. The depth and diameter of such a void would need to be extreme. Satellite missions have confirmed the cold spot repeatedly. The Wilkinson Microwave Anisotropy Probe first mapped it in 2004. The Planck mission, with higher sensitivity and angular resolution, validated its existence and geometry in 2013. Surveys of galaxies along the line of sight reveal a large underdensity known as the Eridanus supervoid. Its scale, hundreds of millions of light-years across, makes it one of the largest void-like features observed. Yet the measured void does not fully account for the cold spot's magnitude. Simulations of photon travel through voids predict temperature deficits smaller than what is observed. Even after accounting for cosmic variance, the anomaly persists. The supervoid explanation remains the most conservative, but it is not complete. Some researchers propose that the cold spot is a statistical outlier, rare, but not impossible. Others consider early universe origins, a primordial texture left by inflation, or a remnant of a topological defect. The most speculative proposal suggests a collision between our inflationary bubble and another region of spacetime during the universe's earliest expansion. In such a model, the cold spot is a bruise left by an encounter that occurred long before stars formed, encoded permanently into the microwave background. None of these interpretations have reached consensus. The available data do not distinguish clearly between coincidence, foreground influence, and exotic cosmology. The cold spot is a single irregularity in the universe's oldest light. It offers no message and no answer, only the reminder that even the earliest maps of the cosmos come with imperfections we cannot smooth away. When the James Webb Telescope looked backward in time, it found spirals and clusters that should not exist that early. The universe had only just cooled from its birth, yet these galaxies already looked ancient. Our models of cosmic evolution wavered like mirages under new light. In standard cosmology, galaxies grow gradually. The first stars ignite a few 100 million years after the Big Bang. Small protogalaxies merge into larger structures over billions of years, accumulating mass through accretion and collisions. Early galaxies should therefore appear small, irregular, and metal-poor. The James Webb Space Telescope challenged this expectation. Images captured at redshifts between z=7 and z=13, when the universe was less than 500 million years old, revealed galaxies with stellar masses comparable to the Milky Way. Some exhibited rotational structure and disk formation, usually associated with far more mature systems. Their existence is not a single anomaly, but a population that appears consistently across early epochs. Galaxy growth is governed by the availability of gas, its cooling rates, and the influence of dark matter halos. Hydrogen clouds collapse under gravity, forming stars that enrich the surrounding medium with heavier elements through supernova explosions. This feedback process slows star formation over time. Large galaxies are thought to emerge from repeated mergers of smaller fragments. Simulations predict that assembling 10 to the power of 10, 10 to the power of 11 solar masses of stars should take billions of years. Yet several JWST targets exceed these masses in a universe only a few 100 million years old. To reach such densities, gas would need to condense far more efficiently, or initial conditions would need to permit extremely rapid formation before feedback mechanisms could suppress growth. The scale suggests either unknown efficiencies or structural conditions absent from current models. JWST's near-infrared instrumentation detects wavelengths stretched by cosmic expansion. By observing redshifted starlight, astronomers identify the age and distance of early galaxies. Spectroscopy has revealed strong emission lines associated with ionized oxygen and hydrogen, indicating active star formation. Several objects show disk-like rotation inferred from velocity gradients, as if they had already settled into organized structure. Their luminosity functions are brighter than anticipated, and their stellar populations appear more massive than permitted by standard formation timelines. These findings are not dependent on a single calibration. Multiple independent surveys, CEERS, GLASS, JADES, report similar mass estimates. While uncertainties remain in dust modeling and initial stellar populations, the overall trend persists. Galaxies appear too large, too soon. There are several paths forward. Some researchers argue that mass estimates may be inflated because early stellar populations produce more light per unit mass than present-day stars. Others suggest that dark matter halos formed earlier or faster than predicted, allowing dense gas clouds to collapse rapidly. More radical interpretations consider modifications to cosmological parameters, differing initial density fluctuations, earlier star formation onset, or deviations from the lambda CDM model. None of these proposals have unified support. The observations do not yet overthrow cosmology, but they emphasize that structure formation may be more efficient at high redshift than standard simulations allow. These massive galaxies formed when the universe was still young. Before most stars existed, they do not explain themselves. They simply sit at the edge of time, larger than models expected, waiting for theories to catch up. Some numbers do not fit inside the mind. TON 618 weighs more than 66 billion suns. Its event horizon could swallow the solar system whole and leave room for more. TON 618 is a hyperluminous quasar located roughly 10.4 billion light-years away. It was first identified not as an exotic object, but as a radio source in a 1957 Bologna survey. Later spectroscopy revealed a quasar with extreme ultraviolet and optical brightness, powered by a central black hole of unprecedented mass. Quasars are galaxies whose central black holes actively feed on surrounding gas, converting gravitational energy into light. Most active galactic nuclei range from a few million to several billion solar masses. TON 618 exceeds these by an order of magnitude, occupying the extreme upper end of known black hole populations. A quasar shines when material falls toward a supermassive black hole. As gas collapses into an accretion disk, it heats to millions of degrees, emitting radiation across the electromagnetic spectrum. The process can produce jets of relativistic particles, magnetic shocks, and powerful winds that shape the host galaxy. Accretion efficiency is limited by physics. A black hole can only swallow material as fast as radiation pressure allows. The Eddington limit for TON 618 to reach its current mass within the age of the universe, at its observed redshift, its growth must have been prolonged, unusually efficient, or seeded by an early collapse far more massive than ordinary stars. Models of continuous Eddington limited growth struggle to produce 66 billion solar masses within a few billion years, even assuming optimal feeding and no interruptions. The mass estimate for TON 618 is derived from broad emission lines in its spectrum. The width of these lines corresponds to the velocity of gas orbiting near the black hole. Faster velocities imply stronger gravity, and therefore higher mass. Using standard virial methods, the gas clouds near TON 618 appear to be moving at tens of thousands of kilometers per second. Combined with its luminosity, over 100 trillion times that of the Sun, the result indicates a black hole exceeding 6.6 times 10 to the power of 10 solar masses. X-ray measurements and infrared observations support the quasar interpretation rather than alternatives such as gravitational lenses or transient starbursts. The object is not magnified or duplicated, it is intrinsically bright. TON 618 challenges assumptions about how supermassive black holes form. Standard models posit gradual accretion at moderate rates or mergers between galaxies. Both mechanisms operate slowly. To reach 66 billion solar masses requires either exceptional conditions or an early universe environment far more conducive to rapid growth than expected. One possibility is that primordial black holes formed directly from the collapse of enormous gas clouds, bypassing phases of star formation entirely. Another involves sustained periods of super Eddington accretion, where material falls faster than radiation can push it away. These scenarios remain speculative. What is certain is that TON 618 represents a category of growth at the limits of known astrophysics. It is not nearby, and it is not unique by intention. It is simply an object that gathered mass faster than our models predicted, growing until light itself could barely escape its gravity. Its existence reveals how large the universe allows structures to become. Near some galactic cores, rotation becomes so intense that space-time itself is dragged in circles. These Kerr black holes spin with such fury that even light is pulled into orbit. Approach too closely and gravity will not pull you inward. It will wrap you around an invisible drain. A rotating black hole is described by the Kerr metric, a solution to Einstein's field equations published in 1963. Unlike the non-rotating Schwarzschild black hole, a Kerr black hole carries angular momentum. Matter falling into the singularity transfers spin, and collisions or mergers can accelerate rotation further. The result is a compact object that warps space-time not only radially, but azimuthally. Near the horizon, this rotational distortion becomes dominant. Instead of a simple gravitational well, the environment becomes a whirlpool of geometry, where trajectories curve not because of force, but because space-time itself is being pulled around the rotation axis. Spin creates two key regions, the ergosphere and the event horizon. The event horizon is the point of no return, where infalling matter cannot escape. The ergosphere lies outside it, defined by the boundary where space-time is dragged faster than light can counter-rotate. Within the ergosphere, no object can remain stationary relative to the universe at large. Every particle must orbit, carried along by the rotation. Frame dragging, the mechanism responsible, is a relativistic effect in which space-time is literally twisted. The stronger the rotation, the larger the ergosphere, and the stronger the induced currents. This rotation enables exotic processes such as the Penrose mechanism, where particles entering the ergosphere can split, allowing one fragment to fall in and the other to escape with more energy than it arrived with, extracting rotational energy from the black hole itself. Evidence of Kerr-like behavior comes from X-ray spectra, gravitational waves, and accretion disk motion. In systems with active accretion, hot gas forms a luminous disk whose inner edge lies close to the event horizon. High-resolution spectroscopy shows broadened ion emission lines, distorted by Doppler shifts and relativistic effects. These distortions reflect orbital velocities approaching a significant fraction of the speed of light. Consistent with frame-dragged trajectories, NASA's New Star mission measured spin parameters for several supermassive black holes based on these signatures, revealing angular momentum near the theoretical maximum. Gravitational wave detections from LIGO show that when black holes merge, the resulting remnant often spins rapidly, matching the predictions of Kerr solutions. The behavior is not inferred from a single observation. It recurs across multiple independent systems. High-spin black holes influence their environments dramatically. Their accretion disks can form relativistic jets that extend thousands of light-years, powered by magnetic fields interacting with rotational energy. These jets regulate star formation, heat interstellar gas, and shape galactic evolution. The most extreme examples exist at the centers of galaxies, where the cumulative effects of accretion, mergers, and inflow spin black holes up over cosmic time. Their rotation becomes an energy reservoir equal to billions of years of stellar output. The mechanisms that cap spin values remain under study. Theory suggests that material falling in from random directions may slow rotation, while coherent inflow may accelerate it. A Kerr black hole does not whirl because it chooses to. It spins because gravity and momentum leave no alternative. It bends space-time into rotation, and everything nearby follows paths carved into geometry itself. Astronomers once spotted a gravitational lens with no source behind it, a distortion drifting like a ghost. A runaway black hole, flung from its galaxy, wandering through the void. Nothing marks its path but the bending of other stars' light. Most black holes remain bound to the gravitational wells that formed them. Stellar clusters, binary systems, or galactic cores. A smaller population becomes unbound, traveling alone through interstellar or intergalactic space. These are runaway or rogue black holes. Without accretion, disks, or companion stars, they emit no radiation. Their existence is inferred indirectly through their gravitational effects. Until recently, such objects were theoretical. Then, astronomers identified a moving lens in the Milky Way, a distortion in starlight consistent with a dark, massive body crossing our line of sight. Its motion and mass suggested a solitary black hole traveling through the galaxy. A black hole can be set adrift in several ways. Asymmetric supernova explosions impart momentum to the collapsed core, producing natal kicks of tens to hundreds of kilometers per second. Binary systems can eject remnants if mass loss destabilizes orbits, leaving the compact object to escape. Black hole mergers can produce even stronger effects. When two massive black holes coalesce, gravitational waves radiate energy asymmetrically. The recoil pushes the remnant in the opposite direction, sometimes exceeding 1,000 kilometers per second, fast enough to leave its host galaxy. A solitary black hole then follows a ballistic trajectory, interacting only through gravity. Without material to accrete, it remains invisible. In 2022, a microlensing event near the galactic bulge was observed by Hubble and the Gaia Observatory. A background star brightened and shifted position over several hundred days, following a smooth light curve characteristic of gravitational lensing. No visible lensing object was present. Astrometric data indicated a mass of roughly 7 solar masses. The source moved through space at approximately 160 kilometers per second, too fast to be an ordinary foreground star. No X-ray emissions, infrared signatures, or spectral lines were detected. The simplest interpretation was a stellar mass black hole passing between us and the background star. It did not orbit anything. It was not part of a binary. It was a compact object traveling through galactic space. Runaway black holes may be common. Stellar evolution models predict that millions of black holes should populate the Milky Way, most unilluminated by accretion. Many would be relics of ancient supernovae. Others could be merger remnants, expelled from galactic centers or dense clusters. Their detection is limited by chance alignment. Only when a rogue black hole passes in front of a distant star, within a narrow angular window, does its mass reveal itself through lensing. Such events can last months or years, depending on mass and relative motion. Even then, measurement uncertainties leave only a narrow path to identification. No instrument scans the galaxy continuously at microlensing precision. These objects drift unnoticed, shaping the orbits of stars they pass and leaving no trace once they move on. A rogue black hole is not a predator. It is a remnant, following momentum, imparted long ago, crossing the galaxy in silence. Its presence is known only when starlight bends around it, and then it disappears again into darkness. Some supernovae refuse to die quietly. The star erupts, fades, then erupts again with fresh fury, as if resurrection were part of its physics. Astronomers call them repeating supernovae. Cosmic phoenixes burning twice. A supernova is the terminal event of a massive star. When its core collapses, gravity overwhelms pressure, and the star expels its outer layers in an explosion brighter than an entire galaxy. The event is singular. Once the core collapses into a neutron star or black hole, no second detonation occurs. Yet in 2014, astronomers observed a class of events that appeared to violate this rule. The transient IPTF 1,4HLs brightened, faded, and brightened again over the course of years. Its luminosity fluctuated multiple times, contradicting the typical supernova light curve that decays smoothly after maximum brightness. The phenomenon suggested that some stars might shed energy through repeated partial eruptions. Standard core collapse supernovae are prompted by the failure of nuclear fusion to support gravity. Once iron accumulates at the core, fusion becomes endothermic and the star implodes. But certain stars exceed this threshold in exotic ways. In extremely massive stars, the outer layers may undergo pulsational pair instability. At high temperatures, gamma rays produce electron-positron pairs, reducing radiation pressure. The star contracts, heats rapidly, and detonates a portion of its outer layers. Matter is expelled, but the core remains intact. The star stabilizes, then resumes fusion until another instability triggers a second eruption. The process can repeat multiple times before final collapse, leaving supernova-like brightness peaks separated by months or years. The best studied example is IPTF-14HLS. Initial observations suggested an ordinary Type II supernova with hydrogen-dominated spectra, but unlike normal events that fade in a few months, the luminosity plateaued, dropped, then rose again. Over the next 3 years, the star brightened at least 5 distinct times. Its spectrum did not show clear signs of interacting with circumstellar material, which might explain secondary luminosity peaks. Historical records revealed a 1954 explosion in the same region, implying the same star may have detonated decades earlier. No established model predicted a star producing explosive outbursts over such long intervals without collapsing fully. Other candidates include SN2009IP and SN2015BH. Both produced major eruptions prior to their final supernova. In these cases, the earlier events appear to have expelled large amounts of mass without destroying the core. Their light curves show irregular bursts, some thought to be giant eruptions rather than true supernovae, but their final detonation aligns with full core collapse. These observations reinforce the concept that certain massive stars can undergo multiple catastrophic shedding events before death. Pulsational pair instability offers the most consistent framework. Stars exceeding roughly 140 solar masses can experience partial disruptions that mimic supernova brightness. Each eruption ejects shells of material that may collide with later ejecta, producing renewed luminosity. This model explains multi-peak curves, but does not resolve every detail of IPTF-14HLS, especially its duration. Alternative theories consider episodic fallback accretion onto a new compact core or magnetar-driven energy injection prolonging brightness. Observations remain sparse because these stars are rare and their outbursts occupy timescales that exceed most survey windows. Their rarity limits statistical certainty, forcing models to compete without decisive evidence. Some stars do not collapse in a single act. They expend themselves in stages, each eruption marking another step toward irreversible failure. Their final state is no different, but the path there is longer than expected, written in repeated flashes against the dark. The galaxy M82 burns with newborn suns, thousands every year. Plumes of plasma rise from its heart like volcanic smoke, painting curtains of red across the void. Starbirth and destruction blur together in a furnace of cosmic time. Messier 82, also known as the Cigar Galaxy, lies about 12 million light-years away in the constellation Ursa Major. It is a starburst galaxy, a system forming stars at a rate significantly higher than average. While the Milky Way produces only 1 or 2 solar masses of stars per year, M82 generates dozens. Observations reveal dense regions of gas and dust compressed into stellar nurseries where gravitational collapse proceeds rapidly. Unlike typical spiral galaxies, M82 exhibits chaotic structure in its central regions, distorted by gravitational interaction with its neighbor, M81. This interaction likely triggered its starburst phase, funneling material into its core. Starbursts occur when gas becomes concentrated beyond a critical threshold. In M82, tidal forces from M81 compress giant molecular clouds, accelerating their collapse. Gravity pulls the gas inward, forming clusters of massive stars. These stars evolve quickly, burning through nuclear fuel in millions of years rather than billions. Their supernovae inject energy into the interstellar medium, creating shockwaves that compress additional gas and perpetuate the cycle. The cumulative energy output drives a galactic wind, hot plasma accelerated perpendicular to the disk. This outflow can reach thousands of kilometers per second, expelling metal-enriched material into intergalactic space. The process enriches surrounding regions with heavy elements and regulates star formation over long periods. Multi-wavelength observations reveal M82's complexity. In optical wavelengths, the central region glows with hydrogen emission lines produced by ionized gas. Infrared imaging shows dense concentrations of dust, obscuring embedded young stars, indicating ongoing formation. Radio data trace molecular clouds and supernova remnants. X-ray telescopes detect hot gas in the galactic wind, confirming the outflow's energy. The Hubble Space Telescope resolves star clusters only a few million years old, containing thousands of massive stars. These clusters are compact and gravitationally bound, suggesting efficient formation. Observations also show filamentary structures extending well above the disk, representing gas pushed outward by feedback processes. The galaxy is not simply forming stars, it is restructuring itself. M82 is a reference point for studying how galaxies evolve during high-activity phases. Starbursts cannot last indefinitely. They exhaust available gas or expel it via winds, eventually halting the cycle. Models predict that M82 will produce most of its stars within a short episode, after which it will quiet into a more stable form. Understanding this process helps contextualize galaxies at high redshift, where rapid formation was common. The powerful winds from M82 transport metals into the intergalactic medium, influencing future star systems in nearby space. The galaxy also illustrates how external interactions, not just internal dynamics, shape stellar populations. Without M81's gravitational pull, M82 may have remained an ordinary spiral with modest formation rates. Messier 82 is not unique in intent. It is simply a place where gravity and gas meet in the right proportions, forcing matter to ignite. It builds stars quickly, then releases them to the universe. Around young stars, dust and rock gather to form worlds. But some stars spin too violently, shredding their own planets before they can mature. Their embryos melt back into the disk, devoured by the parent that created them. Planet formation begins in protoplanetary disks, flattened rings of gas and dust orbiting newborn stars. Over time, grains collide, stick, and grow into planetesimals. These merge into planetary embryos that can accrete gas or develop rocky interiors. The process usually unfolds over millions of years, producing stable solar systems, yet not all disks survive long enough to complete this progression. Some stars rotate so rapidly or radiate so intensely that newly formed bodies are torn apart or heated to destruction before they can finish forming. Observations of young stellar systems show gaps where planets should exist, not because they were never born, but because they failed to survive early conditions. A star's radiation and stellar wind exert constant pressure on surrounding material. In moderate environments, this pushes dust outward and regulates growth. In extreme environments, it becomes a destructive force. Rapid stellar rotation produces strong magnetic fields that channel gas flows and generate energetic outbursts. Young stars, particularly T Tauri stars, exhibit intense flaring events that bathe the disk in ultraviolet radiation. These flares heat and ionize the material, stripping atmospheres and melting solid surfaces. Embryonic planets drawn too close are subjected to tidal forces that deform or disintegrate them. Even beyond the immediate stellar surface, orbital shear can grind material into fragments, effectively recycling failed bodies back into the disk. The system V1298 Tau provides a clear example. It hosts multiple young planets, all orbiting close to a star estimated at less than 20 million years old. The planets show inflated radii, weak atmospheric escape signatures, and unstable orbital evolution. These traits imply intense stellar irradiation, actively reshaping their structure. Other systems exhibit evidence of destruction rather than survival. Infrared observations of stars such as RZ Piscium reveal sudden drops in brightness attributed to collisions or planetary disruption, with excess dust appearing afterward. These debris signatures do not resemble gradual disk clearing, they resemble catastrophic events. In extreme cases, spectroscopic measurements detect metals in stellar atmospheres, thought to originate from infalling planetary matter that has been stripped and accreted. Stars that eat their planets do so through normal physics, not intent. Their radiation environments and magnetic fields exceed the tolerance of nearby formation material. Systems like these complicate models of planetary survival. If destructive stellar behavior persists for millions of years, few planets can reach stable maturity. Some researchers propose that many systems form more terrestrial planets than they ultimately retain, losing the majority in early eras. Others suggest that planetary systems migrate outward or inward, encountering hazards that erase entire generations of worlds. This dynamic evolution implies that the planets we observe today are the survivors, not evidence of typical outcomes, but of selection. Stars create worlds, and some undo them. The process leaves no record except the dust that returns to orbit. Planetary systems that endure are not inevitable. They are simply the ones that were not destroyed. Kepler 10b hugs its star so tightly that half of it never sees night. The surface is a boiling ocean of magma, glowing orange like spilled furnace light. Rocks do not cool there, they ripple like waves in a windless sea. Kepler 10b orbits a G-type star roughly 560 light-years away. It is classified as a lava planet, a rocky world whose proximity to its star drives surface temperatures high enough to melt silicates. The planet completes an orbit in only 0.84 Earth days, placing it in a class of ultra-short period exoplanets. Its diameter is about 1.4 times that of Earth, with a mass roughly 3.7 times greater. Because its orbital period is so small, tidal forces have locked its rotation. One hemisphere faces the star permanently, while the other remains in perpetual darkness. The result is a world divided not by geography or weather, but by a continuous thermal boundary. Tidal locking ensures that the dayside absorbs energy continuously. Temperatures on the illuminated hemisphere exceed 2,500 Kelvin, enough to liquefy basalt and other rocky minerals. Instead of a crust, Kepler 10b likely hosts a molten surface layer, forming a planet-wide magma ocean. The atmosphere that forms above such conditions is not composed of water vapor or nitrogen. It is a thin envelope of minerals. Silicates vaporize under extreme heat, creating a rock-based atmosphere that rises, circulates, and condenses. Winds driven by pressure gradients can carry vapor toward the terminator, where cooler temperatures cause it to fall back to the surface. Volatile substances do not cycle as weather, rock does. The night side may be significantly colder, potentially solidifying the crust, but because tidal locking prevents rotation, heat does not distribute evenly. Thermal conduction through the mantle may moderate extremes, yet the contrast remains fundamental. A molten hemisphere directly irradiated by the star, and a darker hemisphere shielded from continuous heating. Models predict that surface flows are dominated by convection currents within the magma ocean, regulated by viscosity and gravitational pull rather than atmospheric dynamics. Kepler 10b was discovered by transit photometry. As it passes in front of its host star, the reduction in starlight reveals its size. Follow-up radial velocity measurements determined its mass and confirmed its rocky composition. Thermal phase curves, brightness changes, measured at different orbital positions, indicate an extraordinarily hot day side with minimal heat transfer to the night side. These observations are consistent with bare rock or magma facing the star, lacking thick atmosphere to distribute heat. Infrared studies do not show signatures of water, methane, or hydrogen envelopes. Instead, they align with a high-density terrestrial world exposed to intense stellar irradiation. Kepler 10b is not unique. Similar worlds, CoRoT T7b, 55 Cancri e, and Kepler 7-8b, suggest that rocky planets close to their stars follow predictable evolutionary paths. Many begin as larger objects, losing volatiles through atmospheric escape. Solar wind strips their outer layers, leaving dense cores behind. Once close enough, the heat liquefies their surfaces. These planets are laboratories for understanding rock vaporization, mineral atmospheres, and extreme geophysical equilibrium. They also challenge intuitive views of habitability. Not all solid planets resemble Earth, and not all rocky worlds become stable landscapes. Some settle into states governed entirely by thermal physics, with no seasons, oceans, or weather cycles. A lava world does not change its conditions. It faces its star forever, its surface held molten by proximity alone. It is a reminder that planets are shaped by their orbits as much as by their composition, and some never cool at all. On WASP 7-6b, temperatures soar so high that iron evaporates. Winds carry the metallic vapor to the night side, where it condenses and falls from the sky as molten metal. Picture a storm of liquid steel tracing red rivers through charcoal darkness. WASP 7-6b is a hot Jupiter orbiting a star about 640 light-years away in the constellation Pisces. Hot Jupiters are gas giants that orbit extremely close to their stars, often completing a revolution in a few days or less. WASP 7-6b has an orbital period of 1.8 Earth days and is tidally locked. One hemisphere faces perpetual daylight, receiving constant radiation, while the opposite hemisphere remains in permanent night. The proximity to its star raises atmospheric temperatures beyond 2,400 Kelvin, hot enough to vaporize metals that ordinarily exist only in solid or liquid states on rocky planets. The planet does not resemble Jupiter in climate or chemistry. It is a high-temperature environment where planetary weather is governed by mineral physics. The dayside atmosphere of WASP 7-6b heats to temperatures that dissociate molecules and ionize heavy elements. Iron becomes gaseous and mixes with other metallic vapors. Winds, driven by large pressure gradients, transport this material toward the terminator, the transition zone between day and night. In hot Jupiter atmospheres, wind speeds can exceed kilometers per second due to the intense difference in thermal energy. As gas reaches the cooler night side, temperatures drop hundreds of degrees, enough for condensation to occur. Instead of water vapor forming clouds, iron vapor condenses into droplets and falls. The mechanism resembles ordinary rain, but the condensing species is metal, not water. The exact form of precipitation depends on atmospheric depth. At higher altitudes, droplets may crystallize. At deeper layers, molten iron may remain liquid before falling into the lower atmosphere. Unlike terrestrial storms, which involve condensation of volatile compounds, this system operates continuously, driven by persistent irradiation and tidal locking. There is no seasonal cycle. The planet's weather is set by orbital geometry. Evidence for iron condensation on WASP 7-6b comes from spectroscopy. When the planet transits its star, a portion of starlight passes through its atmosphere, imprinting the signatures of chemical elements. Instruments on the Very Large Telescope detected strong absorption lines associated with neutral iron on the evening limb. The region moving from day into night, but those lines disappeared on the morning limb. This asymmetry indicates that iron exists in vapor form on the hot day side, is transported to the night side, and condenses there. Other spectral features, such as sodium and calcium, support the presence of high-temperature chemistry. These findings are not isolated. Different teams, using independent datasets, have reproduced the phenomenon, strengthening the interpretation. WASP 7-6b demonstrates how exotic planetary climates can become when radiation dominates over internal heat and atmospheric composition. Its environment challenges intuitive notions of weather and geology. On Earth, minerals are stable solids. On WASP 7-6b, they serve as mobile components of gas circulation. The planet's behavior suggests that many hot Jupiters may undergo similar condensation cycles involving metals or silicates, each determined by temperature and elemental abundance. Such systems provide insight into atmospheric dynamics under extreme conditions where chemistry and fluid mechanics intertwine. They also clarify how close-in gas giants evolve. Heavy elements may redistribute across hemispheres, altering atmospheric composition, cloud formation, and long-term energy balance. In the absence of oceans or seasons, WASP 76b operates on a simple rule. Metals rise, cool, and fall again. The planet does not correct or adapt. It cycles iron endlessly, following physics imposed by its orbit. GJ 1214b is not ocean as we understand it. Its waters exist in superheated phases, crushed into states beyond ice, vapor, or steam. Beneath its clouds, pressure reshapes liquid like stone, forming oceans deeper than continents. GJ 1214b orbits a small red dwarf star about 48 light-years away in the constellation Ophiuchus. It is classified as a sub-Neptune, larger than Earth but smaller than Uranus. Its mass is about 6.5 Earth masses, with a radius roughly 2.7 times that of our planet. This combination suggests a thick envelope of volatile material above a rocky or ice-rich interior. The planet completes an orbit every 38 hours, placing it extremely close to its host star. Its equilibrium temperature exceeds 530 Kelvin, eliminating the possibility of surface oceans or terrestrial atmospheres like those on Earth. Instead, GJ 1214b exists in a regime where water behaves differently under immense pressure and persistent heat. At the temperatures expected on GJ 1214b, water does not separate neatly into solid, liquid, or gas. As depth increases, pressure drives phase transitions that produce states unfamiliar to everyday experience. Supercritical water, a phase where liquid and gas become indistinguishable, may fill much of the planet's outer layers. Beneath this, pressures in the tens of gigapascals could create exotic ices such as Ice 7 or Ice X, crystalline structures that form only under extreme compression. These phases are solid not because of cold, but because molecular bonds reorganize under stress. If the planet retains a rocky core, heat from formation and tidal interactions with its star may create convection, cycling material upward. Unlike gas giants, the dominant volatile is not hydrogen or helium. It is water in forms that cannot exist naturally on Earth's surface. GJ 1214b has been studied extensively using transit spectroscopy. When the planet crosses its star, starlight filters through its atmosphere, revealing chemical signatures. Early observations suggested a featureless spectrum, implying a thick cloud layer or haze blocking deeper layers. Later, the James Webb Space Telescope detected strong absorption consistent with water vapor, methane, and carbon dioxide, confirming a hydrogen-rich atmosphere dominated by volatiles. Infrared phase curves show low day-night temperature contrast, indicating that heat circulates efficiently through dense atmospheric layers. No surface features have been detected. The planet appears enveloped in a uniform envelope of gas and clouds. These data support the sub-Neptune interpretation, a world with deep volatiles rather than an Earth-like interior. GJ 1214b helps define a category of planets that do not resemble anything in our solar system. Sub-Neptunes are common in galactic surveys, yet we lack a local analogue to study. Their atmospheres blur the boundary between terrestrial planets and gas giants. If conditions on GJ 1214b once permitted oceans, they have since been transformed by irradiation into exotic fluids and compressed ices. Some models propose that such planets form beyond the snowline, accumulate water-rich material, and migrate inward. Others suggest they form in situ, accumulating volatiles from protoplanetary disks. Regardless of origin, their evolution is dictated not by surface geology, but by deep chemistry under crushing pressure. GJ 1214b does not resemble the oceans humans imagine. Its waters do not flow or freeze. They transform into unfamiliar states under the weight of their own planet. It is a reminder that even the simplest substance behaves differently when gravity and heat rewrite its rules. Across a solar system, only 40 light-years away, lies 55 Cancri E, a planet so close to its sun that its surface never cools. Silica vapor circulates in roaring winds like molten breath, condensing into razor-sharp crystals that fall sideways at hurricane speeds. Imagine a horizon that glitters like shattered mirrors, endlessly recycling its own broken body. 55 Cancri E orbits a star similar to the Sun, but does so at an extraordinary distance, roughly 0.015 astronomical units. It completes a full orbit in just 18 hours, qualifying it as an ultra-short period exoplanet. The planet is tidally locked, exposing one hemisphere to permanent daylight and leaving the other in unending night. Both conditions produce extreme temperature gradients. The day side can exceed 2,400 Kelvin, hot enough to vaporize rock-forming minerals such as silica. The planet is roughly twice Earth's radius and 8 times its mass. With a density that suggests a rocky composition rather than a gas giant envelope. With no stable surface water or thick atmosphere, its environment is controlled primarily by mineral physics. Silicates that would be solid under terrestrial conditions become gaseous on 55 Cancri E's day side. With intense irradiation, minerals sublimate into vapor, forming an atmosphere composed of rock-based species rather than water or nitrogen. Tidal locking establishes persistent thermal gradients. Hot vapor flows toward the twilight zone, where temperatures fall sharply. In this region, silica condenses into solid particles. Wind speeds may reach several kilometers per second due to pressure differences between the two hemispheres. The condensation forms microcrystals or glassy flakes that are carried laterally in high-speed jets, ultimately raining sideways across the night side. The process does not require storms or weather in the traditional sense. It results from equilibrium between radiation, vapor transport, and phase change. Atmospheric loss also shapes the planet. Close-in worlds experience strong stellar winds and UV irradiation, stripping light elements. Heavy minerals remain, increasing the atmospheric proportion of refractory species. This feedback may reinforce silica cycling, while suppressing volatiles that could moderate climate. Evidence comes primarily from phase curve measurements and spectroscopy. Space telescopes such as Spitzer and Cheops have captured the planet's thermal emission at various orbital stages. The day side glows brightly in the infrared, while the night side appears significantly cooler. The temperature contrast implies limited heat redistribution, consistent with mineral-rich atmospheres rather than hydrogen-dominated ones. Observations reveal spectral features associated with silicates, suggesting rock vaporization. High brightness at secondary eclipse, when the planet passes behind its star, indicates continuous heat input and a surface exposed to intense radiation rather than a thick insulating atmosphere. The absence of water signatures in spectral data further supports a mineral-based atmospheric model. 55 Cancri E is often referred to as a lava planet, but its behavior extends beyond molten surfaces. It demonstrates how planetary weather changes when the dominant atmospheric species are minerals. Instead of oceans condensing and evaporating, rocks vaporize and condense. Its silica precipitation cycle may be a template for many close-in rocky exoplanets, each governed by a balance of irradiation, tidal locking, and mineral composition. The planetary interior may also include large quantities of carbon, possibly forming diamond-rich layers under extreme pressure. If so, geological processes would differ from Earth's plate tectonics, responding instead to compressive mineral phases and mantle convection. Whatever its internal structure, the visible environment is dominated by mineral cycling, not habitability. On 55 Cancri E, glass falls not as debris, but as weather. The planet continues its orbit, vaporizing and condensing silica each day, driven by heat it cannot escape. It is a world that never cools, defined by physics alone. Some planets are orphaned, torn from their star systems by violent gravitational encounters. They drift through interstellar night, atmospheres frozen, oceans sealed beneath pressure. No sunrise ever warms them. Yet some may hold internal heat, simmering like secret worlds beneath eternal darkness. Rogue planets, also called free-floating or interstellar planets, are planetary mass objects that do not orbit any star. Instead, they travel through the galaxy on solitary trajectories. They are thought to be common. Simulations of planetary system formation suggest that gravitational interactions, especially in crowded, unstable systems, regularly eject planets into space. Surveys using microlensing techniques have hinted that there may be as many rogue planets as there are stars in the Milky Way, possibly more. These worlds are not bound to a central source of light or heat. They move in darkness, carrying only the energy they retain from their birth or generate internally. Several pathways can produce a rogue planet. In young planetary systems, massive bodies compete for stable orbits. Close encounters between giant planets can transfer enough energy to fling one outward, beyond the reach of the star's gravity. In multiple star systems, shifting gravitational fields can destabilize previously stable planetary orbits. Stellar flybys in dense clusters can also dislodge planets. Once ejected, the planet follows a nearly straight path through interstellar space, influenced only by the galaxy's gravitational potential and distant encounters. Without a star, surface temperatures on such planets plummet. However, they are not necessarily inert. Internal heat from radioactive decay in their cores, residual heat from formation, and potential past tidal heating can maintain warm interiors for billions of years. If a rogue planet retains a thick atmosphere, particularly one rich in hydrogen, it can trap this internal heat. Beneath an insulating atmosphere, or ice shell, subsurface oceans could remain in liquid form even while the surface remains frozen and dark. Detecting rogue planets is challenging because they emit little light. The most effective method so far is gravitational microlensing. When a massive object passes between Earth and a distant star, its gravity bends and amplifies the starlight temporarily. The duration and shape of this brightening can reveal the mass of the lens. Events lasting hours to days, with no detectable host star, are consistent with planetary mass lenses. Surveys like OGLE and MOA have reported such signals, implying a large population of free-floating planets. A few candidates have been imaged directly in the infrared, particularly young, still warm rogue planets in star-forming regions. Objects such as PSOJ 318, 522 appear to be isolated planetary mass bodies, with temperatures of hundreds of Kelvin and masses a few times that of Jupiter. Their spectral signatures show features expected of gas giant atmospheres, but without a nearby star to orbit. Rogue planets complicate the definition of planetary systems. They demonstrate that planet formation is not always a stable process, ending in neat, permanent orbits. Many systems may lose a fraction of their planets during early dynamical reshuffling. For astrobiology, rogue planets raise a quiet possibility. Life may not require sunlight if internal heat and chemistry are sufficient. A thick atmosphere or ice shell could shield a subsurface ocean, allowing liquid water to exist far from any star. Such worlds would be extremely difficult to detect, much less study, but they expand the range of environments where complexity might arise. Rogue planets travel unseen between the stars, carrying their histories with them. They do not mark dawns or seasons, only time measured in orbits around the galaxy. Whether their interiors are frozen or warm, they exist regardless of observation, drifting through a darkness that never ends. A dead star, crushed into a sphere the size of a city, spins hundreds of times per second. Its magnetic poles sweep space with beams of radiation, like a cosmic clock ticking faster than any mechanical device. Time becomes rhythm carved from collapsed matter. A pulsar is a neutron star, the remnant core of a massive star that has undergone supernova collapse. When the outer layers of a large star are expelled, gravity forces the remaining matter inward until protons and electrons merge into neutrons. The resulting object packs more mass than the Sun into a sphere roughly 20 kilometers across. These remnants often rotate rapidly because angular momentum is conserved during collapse. What once was a slowly turning stellar core becomes a compact object spinning dozens to hundreds of times per second. If its magnetic axis is tilted relative to its rotational axis, beams of radiation sweep outward in a lighthouse pattern. To a distant observer, each sweep appears as a pulse. Pulsars generate radiation through intense magnetic fields. Their surfaces host magnetic fields trillions of times stronger than Earth's. These fields accelerate charged particles along the poles, producing beams of radio, optical, X-ray. The beams are narrow, so only observers aligned with them detect the pulses. The rotation is so stable that pulsars rival atomic clocks in precision. Their signals arrive with microsecond accuracy across thousands of light years. Over time, pulsars lose rotational energy. They slow gradually, emitting less radiation, but the rate of change is predictable. This spin down can be used to measure age, magnetic strength, and energy loss. Some pulsars exhibit glitches, sudden increases in rotation rate. These are thought to arise from interactions between the star's superfluid interior and its rigid crust. In normal cooling, the crust slows, while the interior retains angular momentum. When stored momentum transfers outward, rotation jumps abruptly. The pulsar then resumes its slow decay. The process highlights the extreme physics in neutron stars: superfluidity, nuclear density, and crustal cracking under immense stress. Pulsars were first detected in 1967 by Jocelyn Bell Burnell and Anthony Hewish. They recorded radio pulses arriving every 1.3 seconds from a fixed point in the sky. The precision ruled out terrestrial interference. For a short period, the signal was nicknamed LGM-1, Little Green Men, because no known natural source pulsed so cleanly. Soon, additional pulsars were discovered, confirming a widespread astrophysical phenomenon. Timing arrays measure their pulses to study gravitational waves, test general relativity, and probe interstellar electron densities. The millisecond pulsars, objects rotating hundreds of times per second, are especially stable. Some are thought to be recycled, neutron stars that gained angular momentum by accreting material from a companion. Pulsars serve as navigational markers in astrophysics. Their predictable timing allows spacecraft to determine position in space without reference to Earth, using triangulation from pulse arrival times. They also anchor cosmological measurements. Binary pulsars have provided indirect evidence for gravitational waves decades before direct detection, as their orbits decayed at rates predicted by general relativity. Young pulsars, embedded in the remnants of their parent explosions, provide clues to the life cycles of massive stars. The diversity of pulsar types, isolated, binary, magnetar adjacent, reflects a continuum of collapse outcomes. They demonstrate how matter behaves when stripped of ordinary chemistry and compressed to nuclear densities. A pulsar does not illuminate space out of intention. It spins and sweeps radiation because collapse left no other form of balance. Its rhythm endures across centuries, marking time in pulses long after the star itself has died. Buried in the halo of the Milky Way is SMSS J0313-6708, a star formed nearly from pure hydrogen and helium. It carries no metals, no fingerprints of the generations of stars that should have preceded it. Astronomers call it primordial, a fossil left over from when the universe was still young and silent. SMSS J0313-6708 lies roughly 6,000 light-years away. It is part of the galactic halo, a diffuse sphere that surrounds the Milky Way's disk. Unlike the spiral arms, the halo contains some of the oldest stars known. They formed before the galaxy fully assembled, preserving conditions that predate most stellar generations. Modern stars show traces of heavy elements, carbon, oxygen, iron, produced by earlier stars. Astronomers call these elements metals, even when they are not metals in the chemical sense. SMSS J0313 3-6708 has so few metals that instruments barely register them. Its spectrum lacks the signatures of iron almost entirely, placing it among the most metal-poor stars ever found. A star's chemical imprint reveals its ancestry. The first stars, population 3 stars, formed directly from primordial hydrogen and helium left by the Big Bang. They were massive, short-lived, and unstable. When they died, they seeded surrounding gas with heavier elements created through nuclear fusion. Later generations formed from this enriched material. With each cycle, the universe accumulated metals. SMSS J031 3-6708 appears to have formed from gas that remained nearly untouched by this process. Its composition indicates that it arose immediately after one or perhaps only a few supernovae, at a time when metals were scarce. The absence of iron suggests enrichment from a specific kind of supernova, one that expelled lighter elements like carbon while trapping iron within the collapsed core. The star is a red giant today, having exhausted hydrogen in its core. Its long life owes to its low mass. Massive stars burn quickly and collapse within millions of years. Low-mass stars persist for billions, outliving entire galactic eras. Because of its nearly pristine chemistry, SMSS J031 3-6708 may be more than 13 billion years old, formed shortly after the first galaxies assembled. The SkyMapper telescope in Australia conducted a survey to identify extremely metal-poor stars. SMSS J031 3-6708 stood out because the absorption lines of iron, normally visible even in ancient stars, were absent. Follow-up spectroscopy using the Magellan telescopes and the Very Large Telescope confirmed the result. The star's iron abundance is less than 1/10,000,000th that of the Sun. In contrast, its carbon levels are relatively elevated. This imbalance is a signature of selective enrichment, consistent with supernova models in which heavier elements remain trapped. The absence of iron lines was not a measurement artifact. It was the defining characteristic of the star. SMSS J0313 3-6708 is not literally older than the Milky Way in age, but it formed before the galaxy reached its present structure. It preserves conditions from a transitional era when the universe moved from primordial chemistry to enriched environments. Such stars serve as time capsules. They test theories of early supernovae, nucleosynthesis, and galaxy formation. Their existence suggests that the first stellar generations were not uniform. Some enriched their surroundings selectively, producing pockets of gas capable of forming low-mass stars that would survive to the present. These survivors constrain models of population 3 star behavior, objects never directly observed but inferred from the fingerprints they left behind. The star does not advertise its age. It burns slowly, unchanged across epochs, carrying within its spectrum the silence of the early universe. In a galaxy built from countless deaths and rebirths, it remains a witness to the time before almost everything else existed. Some theorists believe the universe could carry wounds from its earliest moments, infinitely thin filaments heavier than stars. If they exist, they could slice through space like razors, bending light and matter as if the universe itself had torn. Cosmic strings are hypothetical one-dimensional defects formed in the early universe. They arise in certain models of symmetry breaking, moments when fundamental forces separated as the cosmos cooled. Before these transitions, the universe may have existed in a unified state where physical fields were symmetrical. As temperatures fell, symmetry fractured into distinct phases, similar to how water crystallizes into ice. In some scenarios, the boundaries between these phases cannot be completely smoothed away. The leftover structures become topological defects, frozen into space-time. Unlike familiar strings made of matter, cosmic strings are defects in the fabric of the universe itself. They would be extremely narrow, possibly thinner than an atomic nucleus, yet incredibly dense. Cosmic strings would store enormous energy per unit length. Their tension, called mu in theoretical models, would be so high that it is often expressed as a fraction of the speed of light squared. A single string could have more mass per centimeter than Mount Everest. Their tension would cause them to pull taut, like stretched elastic. When two segments intersect, they could reconnect, snapping apart into loops. These loops would shrink as they radiate gravitational waves, slowly losing energy. The process is not explosive, it is gradual, governed by general relativity rather than chemistry or fusion. If strings exist, they would not affect local environments like stars or planets. But at cosmological scales, their gravity could distort light, matter, and space itself. Unlike ordinary gravitational objects, cosmic strings would not pull from a central point. Their influence would resemble a wedge cut from space-time. A particle passing near the string would experience a sideways deflection. Light would bend, but not because of mass in a spherical volume, because space around the string would be geometrically altered. No cosmic string has been conclusively identified. Observations focus on indirect signatures. One approach is gravitational lensing. A string would split background objects into duplicate images, separated by a thin, linear distortion. Unlike lensing by galaxies, which produces arcs or halos, string lensing would appear as sharp parallel duplicates. Surveys occasionally report candidates, but none have survived rigorous confirmation. Another strategy involves gravitational waves. String loops should emit gravitational radiation as they shrink. These signals would appear as background noise detectable by observatories such as LIGO, Virgo, or pulsar timing arrays. Some recent experiments have detected stochastic gravitational wave backgrounds, but their origin remains uncertain. Dark matter distributions and the CMB have also been examined for telltale imprints. So far, results constrain the possible tension of strings, but do not prove their existence. Cosmic strings would be relic markers of physics beyond the standard model. They would tie modern cosmology to early universe symmetries and high-energy particle theories. Their existence could support frameworks such as grand unified theories or particular inflationary models. They would not be dangerous in a human sense. Their density does not imply interaction with biological matter, yet their presence would reshape our understanding of how space-time evolved from a hot primordial plasma to the structured cosmos we inhabit. They would function as fossils, not of stars or galaxies, but of the universe itself. If cosmic strings exist, they are not scars from violence. They are remnants of transition, trapped in space-time after forces diverged. The universe reveals its past unevenly, and some of its earliest marks may run straight through the dark, unseen and indifferent, cross the threshold of a black hole, and information itself can no longer return. The event horizon marks the point around a black hole where escape becomes impossible. It is not a solid surface or a membrane, but a boundary in space-time geometry. Inside it, all trajectories, no matter the speed, lead inward, not even light, the fastest signal in nature. Black holes form when matter collapses under its own gravity, compressing mass into an incredibly small region. For stellar mass black holes, this collapse is triggered by the core death of massive stars. For supermassive black holes, the processes are broader. Mergers, gas accretion, or primordial origins. Whatever the mechanism, once sufficient mass is confined within a critical radius, an event horizon emerges, defining the region from which no information returns. The event horizon arises from general relativity. A black hole's gravity is not a force pulling downward. It is curvature bending space-time inward. The Schwarzschild radius expresses the distance at which escape velocity reaches the speed of light. Crossing this radius does not alter local physics. An astronaut would feel nothing unusual at the boundary if the black hole were sufficiently large. But from the outside, signals emitted from within appear increasingly redshifted. Photons lose energy as they climb, becoming weaker and slower to arrive, until they vanish entirely. Time dilation also becomes extreme. To a distant observer, An infalling object seems to freeze at the horizon, its final approach stretched across eternity. From the perspective of the falling object, the horizon passes normally and the journey continues inward. Inside, gravity intensifies. In a non-rotating black hole, all paths converge at a central singularity, a point where curvature becomes infinite in classical models. In rotating, or Kerr, black holes, the interior geometry becomes more complex, forming a ring singularity and nested horizons. In either case, no known mechanism allows matter or information to re-emerge. We do not image the event horizon directly as a surface, but we observe its edge through its shadow, regions where light is absent because photons fall inward. The Event Horizon Telescope produced the first image of a black hole silhouette in 2019. The object at the center of the galaxy, M87. The bright ring surrounding the darkness is light from accretion disk material bent by gravity. The central void marks the photon orbit region, beyond which paths dive irrevocably inward. In 2022, a similar image revealed Sagittarius, A star, the supermassive black hole in our own galaxy. Both matches predictions from general relativity, confirming the event horizon's structure indirectly. X-ray flares, orbital precession of stars, and the timing of plasma hotspots near the horizon all provide further constraints. The event horizon may be the most literal boundary in astrophysics, the edge of observable influence. Yet its interior is not fully understood. Quantum mechanics suggests information cannot be destroyed, while classical relativity allows it to vanish. This tension forms the information paradox. Proposed solutions include holographic dualities, horizon-layered structures, or microscopic degrees of freedom encoded at the boundary. What the event horizon makes clear is that gravitational collapse has consequences for the structure of spacetime itself. It is not merely a dark object, it is an endpoint of known physics. The event horizon offers no warning, no resistance. Beyond it lies a region we cannot interrogate, shaped only by gravity and hidden from the universe that remains outside. There is a distance beyond which galaxies will never reach us, no matter how long the universe survives. Their light will keep traveling, but expansion will carry them faster than photons can close the gap. We see their history, but their present is forever lost. The observable universe is limited not by what exists, but by what light has had time to reach us. Since the Big Bang, space has expanded, stretching distances between galaxies. Photons emitted shortly after the first stars formed have been traveling for billions of years, gradually reddened by the expansion of the cosmos. Their arrival defines what we call the observable universe. A sphere centered on Earth, currently about 46 billion light-years in radius. Beyond this sphere lie regions whose light has not yet had time to arrive. They are not hidden because they are dark. They are hidden because space-time has outrun their signals. The universe may be vastly larger than the portion we can see. Cosmic expansion is not motion through space. It is the stretching of space itself. General relativity allows distances between objects to increase, even if they remain at rest, locally. At small scales, gravity and other forces counter expansion, preserving solar systems and galaxies. At cosmological scales, dark energy accelerates it. The expansion rate is described by the Hubble parameter, which determines how fast distant galaxies recede. At extreme distances, recession speed exceeds the speed of light, not because galaxies are traveling faster than light, but because the space between us grows faster than photons can bridge it. This produces a horizon, not a wall, but a limit. Objects beyond this cosmological event horizon are receding so rapidly that no future light they emit will ever reach us. We receive only photons emitted earlier, when they were closer. Their present and every future state lies permanently outside our causal reach. Measurements of distant supernovae, cosmic microwave background radiation, and baryon acoustic oscillations reveal how expansion has changed across cosmic time. In the late 1990s, observations of Type Ia supernovae showed that expansion is accelerating, not slowing. This acceleration is attributed to dark energy, a property of spacetime that exerts negative pressure. The Planck satellite mapped the CMB with high precision, supporting models of a flat universe dominated by dark energy and dark matter. These results imply that the cosmic horizon is not static, it evolves. Galaxies that are visible today at extreme redshifts will eventually slip beyond contact. Their photons, stretched into longer wavelengths, will continue to dim until no observable trace remains. The horizon defines the limit of what humans, or any civilization, can ever know. Galaxies now billions of light-years away will, in the far future, vanish from view not by moving, but by receding past the ability of space to return their light. Only the local group, Milky Way, Andromeda, and their satellites will remain gravitationally bound. Everything else will drift away into unobservable isolation. Cosmology often speaks in terms of total size or age, but the horizon reframes the universe as a collection of disconnected islands, each shrinking in observational scope as time passes. What we see today is a snapshot of what was, not what is. At the horizon, a galaxy becomes memory. Its light continues toward us as a record of a past that no one alive today ever witnessed. Beyond that boundary lies a universe still unfolding, inaccessible not by distance, but by time itself. You have traveled across a universe that reveals itself in fragments, in bursts of radio, in voids without galaxies, in molten worlds locked forever in daylight, in stars that remember an age when nothing else had yet taken shape. It leaves evidence in layers, each piece a relic of processes that began long before any witness existed to record them. Every object we explored tonight carries its own logic. A rogue planet keeps moving because gravity once pushed it from its birthplace. A pulsar spins because collapse preserved its angular momentum. A primordial star burns quietly because low-mass fuel cannot exhaust itself as quickly as its ancestors. None of these phenomena aim to astonish. They persist because physics leaves no alternative path. The black holes we traced are not monsters. They are endpoints of stellar lives, marking transitions in matter and in time. Their horizons are not melodramatic boundaries, but simple consequences of curvature. Space expands not with intent, but because the equations that describe its structure allow it. Even the galaxies drifting beyond our horizon are not lost maliciously. They merely cross a distance where light can no longer compensate for the growth of space-time. In every direction, the universe is older and larger than imagination suggests. Yet it is made from the same particles that form your body, the same matter that once lived inside ancient stars. The iron in blood, the calcium in bone, the carbon in every thought. Each atom was forged in a furnace older than memory. If you feel small, it is not because your life is insignificant. It is because you are part of something that does not measure existence by scale. You were assembled from the same processes that produce galaxies, voids, and the interstellar night. So rest now inside that realization. The universe is not a stranger looking back at you. It is your origin, your chemistry, your inheritance, reflected in starlight that has crossed eras to reach your eyes. Let its distances soften into calm. Let the questions that remain unanswered become gentle reminders that discovery never ends. You are floating within a cosmos that continues, unfolding beyond sight, its patterns slow and indifferent, yet full of meaning for those who pause long enough to see them. Sleep, and let the light of old stars fade into the quiet. The universe will still be there when you wake.